Okay, so welcome everybody to round 3 of the Algebra, Particles, and Quantum Theory seminar series. I'm pleased to introduce to you tonight's speaker, Shadi Tahvildar-Zadeh. Shadi is a professor of mathematics at Rutgers University. He completed his PhD at NYU and next became assistant professor at University of Michigan. Subsequently, he worked as an assistant professor at Princeton before finally signing on with Rutgers University. My first introduction to Shadi was shortly after Donald Trump had been elected as US president. And Shadi gave a defiant, compelling speech at the March for Science, which might still be available online. The day Trump took office, Shadi built his own signs and marched together with the Women's March. And in more recent days, I learned that Shadi volunteered for the International Rescue Committee, an organization that has been helping Afghan refugees after the Taliban overtook the country. Anyone that knows Shadi knows him as someone who puts his money where his mouth is. Shadi is also an exceptional citizen within the mathematical physics community. Currently, he's supervising the research projects of no less than a dozen students. He openly encourages them to pursue their own ideas in physics in spite of the very real career pressure to do otherwise. Given such a character sketch, it might not surprise you to know that Shadi has been unafraid to pursue different lines of research himself, regardless of the current trends. As a case in point, he will tell us today about Bohmian Mechanics, an interpretation of quantum mechanics, which is not currently a mainstream topic. However, for reasons that he may explain for us, it's nonetheless earned itself a loyal following within the quantum foundations community. Now, before we begin, I'd like to emphasize that everybody who showed up today is here to learn. And so I would hope that everyone feels comfortable enough to raise your hand and ask a question throughout the talk if they have one. If you accidentally ask a silly question, of course, it's not a big deal. You just brush yourself off and try again next time. And I would especially like to encourage questions from graduate students, upper level undergraduates, and postdocs. So Shadi, anytime you're ready, go ahead, please.
Well, thank you so much, Cohl, for this introduction. I'll try to live up to it. Talking about Bohmian mechanics this is a big topic, and I do have a lot to say, but in the interest of time, I will go briefly over some topics. So first of all, I'm dedicating this talk to Detlef Dürr, whom COVID took away from us earlier this year. More than any single individual, Detlef was responsible for the advancement of Bohmian ideas, and he was tireless in his efforts. It was perhaps about someone like him that Tennyson said, "One equal temper of heroic hearts, made weak by time and fate, but strong in will to strive, to seek, to find, and not to yield." Here's an outline of my talk. I will first try to explain what do we talk about when we talk about quantum mechanics. I will briefly explain the non-relativistic Bohmian mechanics, and also I will spend some time explaining a relativistic extension of Bohmian mechanics, which is the one that my group here at Rutgers has been busy with for quite some time. And then I will have some concluding remarks. So if you have taken any course in philosophy or have watched any lectures, you know that there is something called ontology, which is the study of what is there. And this is also, there is something parallel to that called epistemology, which is the study of what is knowable, the study of knowledge. So Bohmian mechanics is an ontological formulation of quantum mechanics in the sense that it concerns itself with what is there and tries to talk about real stuff. Every physical theory needs to have a clear primitive ontology. By primitive ontology, we mean what are the objectively real things that the theory is about. The way to get at that, to find out what that is, to ask the about what and the of what question. This is what I tell my students all the time. When somebody tells you that they have something to say about information, ask them information about what? Because information has to be about something. If they talk about a physical quantity like energy and momentum and so on, ask them energy of what? Momentum of what? If they say they have a wave function, say it's a function of what? What is its domain? If they say they have an operator, ask what is it acting on? It's an operator on what? And if they tell you it doesn't matter, insist that no, it does matter. So for Newtonian mechanics, the primitive ontology is point particles with definite positions at all times. This is what the theory is about fundamentally. For Maxwell-Lorentz electrodynamics, it's word lines of point charges in space-time and the electromagnetic field defined in the exterior of those word lines. Of course, whether it works or not, that's a different story, right? Whether you can have a coherent theory that talks about those things, that remains to be seen, of course, but that's what we mean by primitive ontology. In a sense, Bohmian mechanics is about points that move. I will explain what that means. So Bohmian mechanics, also known as Dobrys-Bohm theory or pilot wave theory, it goes by all these names. The primitive ontology of it is point particles, a fixed number of n points in space with positions q sub k of t, positions that depend on time, k from 1 to n. The law of motion of these points, so far that would be just like Newtonian mechanics. The difference is that the law of motion is not Newtonian. It departs from that in two important ways. First of all, it's first order. If you remember anything about Newtonian mechanics, the law of motion is second order because you can take F equals ma and write it as acceleration equals 1 over mass times the resultant of forces acting on the particle. And that's a second order differential equation. Bohmian mechanics, the guiding law for Bohmian mechanics, it's called the guiding law. It gives the velocity of the particle as a function of the positions of all of the other particles. So first of all, this is the first order law. And also you can see that it's manifestly non-local because the velocity of the kth particle doesn't depend just on the position of the kth particle. It depends on the position of all of the particles. All right, where do we get this velocity field? So this velocity field is defined on the configuration space. In other words, the space of all possible configurations of n points in R3. That's a 3n dimensional space, which we denote by R3n. And this V object at any time t is a vector field defined on this configuration space. This V, where do we get this V from? This comes from something called a wave function. So in Bohmian mechanics, there is something called the wave function of the system of n particles has a function associated with it, which is defined at every time t, it's defined on the configuration space and takes its values in a k component complex space. The number k here depends on the spin of the particle. So you can think of this simplest case in case of spinless particles. This would be just complex valued function defined on the configuration space. And this velocity field is defined in terms of the wave function in the following way. The imaginary part of psi dagger times the gradient of psi with respect to the kth variables divided by psi dagger psi times this coefficient in the front, h bar is the Planck constant, and m sub k is the rest mass of the kth particle. So, all right, what about this wave function? This wave function at any given time t, it's an element of a complex Hilbert space. For example, the space of all square integrable functions defined on the configuration space, taking values in the right ck space. It evolves according to the Schrödinger equation. This is the usual Schrödinger equation, the linear Schrödinger equation. So the time derivative of psi times IH bar equals capital H acting on psi, where capital H is the Hamiltonian of the system. It's a self-adjoint operator with some domain D in the Hilbert space. Here's an example, typical example of this Hamiltonian, right? It's a sum of the Laplace operator in the kth variable with these coefficients, plus some interaction potential defined on the configuration space. Okay, so in a sense, this slide, it's all there is to it as far as Bohmian mechanics is concerned. So here you have an evolution equation for the wave function psi. It's an evolution equation, so you need to specify initial data for it. So suppose the initial wave function psi naught is given to you as some element in that domain. Then you solve this Schrodinger equation, right? You find psi at all time t. Then you take that psi and stick it in the right-hand side here inside this V, okay? And that becomes a known vector field on the configuration space. Then you evaluate the vector field on the actual positions of the particles, because particles in this theory have actual positions. And then you have to start with some initial positions, initial actual positions for the particles. And you solve this ordinary differential equation, and that gives you trajectories for the particles at all later times.
Shadi, can I interrupt you for, sorry, for
Go
a second? I think, Tejinder, did you have a question? Oh, I think his hand went down. Okay, it's okay. Maybe he'll put his hand up again.
Yeah, I think maybe it's better to, if you have questions, you can put them in the chat, and then I will stop from time to time and answer those questions, okay? Because it's quite possible that if you wait, your question will be answered further down.
Fair enough.
So, okay, so, right, so given, if this psi naught is given to you, if you know what psi naught is, the initial wave function, and if you have the initial positions of the actual positions of the particles, then you have their position at all later times. So in this sense, Bohmian mechanics is a deterministic theory. So now that may surprise you because you thought that quantum mechanics is not supposed to be deterministic. How does randomness enter in a deterministic theory? Well, in the same way it enters in classical statistical mechanics. It's because those initial conditions are not accessible. So as I was saying is that if you know psi naught fully, and if you know these initial positions, then this is a deterministic theory, but of course you don't, right? Just like in the case of a gas in the box in classical statistical mechanics, if you knew the positions and velocities of every atom of the gas at an initial time, then Newton's equations of motion will allow you to find their positions at all later times. So in that sense, that's a deterministic theory, but of course, only Laplace's demon knows that. And therefore, we have to talk about the statistical features of the theory. So that's in the same sense. Bohmian mechanics is manifestly non-local, meaning distant events influence each other instantaneously. And this is not a bug, this is a feature, as you will see. It's got to be like that because, in fact, it turns out that our world is a non-local world, and we have to live with that. So to the extent that quantum mechanics makes unambiguous predictions, one can show that Bohmian mechanics makes the same predictions. So here's the celebrated example of that, the two slit experiment, which you probably know about. You take a source for electrons, let's say, and you put them behind the screen with two slits in the screen, and you put another screen a distance away with some fluorescent substance is smeared on it so that when an electron lands on the screen, it gives you a dot. And when you do this experiment, you keep sending electrons one after the other. They start to accumulate, and as they form a certain pattern on that screen of bands of light and dark. The picture you're seeing here are the Bohmian trajectories of those particles. So if you actually solve those equations that I showed you, assuming that where does the initial position of the electron being somewhere here or somewhere here, then that's the resulting motion that you would get, right? And notice that this motion, even though there is no force acting on the particles, they are moving in wavy lines. Why is that? It's because they're being guided by the wave function. So even though the electron, because it's a particle that has a definite position, it's not going to go through both holes. That doesn't make any sense. It will either go through this hole or it will go through that hole. But there is a wave function, and the wave function knows about everything, knows about the holes, where they are, and so on. So it's the wave, in some sense, that goes through both holes and interferes with itself and forms these peaks and valleys. And because the wave function is guiding the particle through the guiding equation, that will cause the particles to just obey that and organize themselves in this way. So this is an example of how you get the same predictions of quantum mechanics when quantum mechanics is making unambiguous predictions. However, Bohmian mechanics is even better because it can make predictions in situations when orthodox quantum mechanics fails to make unambiguous ones. One great example of that is the study of arrival times of particles. As many of you know, time is very difficult to define time as an operator. It doesn't fit very well with the operator formalism of standard quantum mechanics. And yet, if it is actually a particle and it has a position at all times, then arrival time, it's very easy to find out by using Bohmian mechanics. In fact, there's this recent article published in Scientific American. The October issue of this year had this wonderful article. Let's see if this works. Oh yeah, it works. So the simple experiment could challenge a standard quantum theory. Measuring the time it takes particles to travel between 2 points may offer the best yet test of Bohmian mechanics. So I urge you to look at this article in Scientific American, and also there's a scientific article that's being cited there, and you can read that to understand the details of that. So, but to make a long story short, Bohmian mechanics is capable of more. It's not just that we repeat the same things that we already knew from a standard quantum mechanics. Bohmian mechanics is a quantum theory without observers. There is no need to talk about observers and observations and things like that. It does not need axioms about measurement or collapse of wave function. Many of these things are actual theorems in Bohmian mechanics that you can derive from the first principles that I mentioned. So all this operator formalism and so on, it emerges, right? You don't need to start with that. And that's very important. So these are a bunch of things that Bohmian mechanics are. Now I'm going to tell you about some things that Bohmian mechanics is not. And the reason I have this slide is that I have heard with my own ears rumors about what Bohmian mechanics is can't do this, you can't do that, or is ruled out by this, or is ruled out by that, and so on. And not just by people who don't know, but also by people who are very well-known physicists, and they have big platforms on social media and so on, and they talk about it. So it's important to note that to answer some of these criticisms. Bohmian mechanics is not just an interpretation of quantum mechanics, it's a completion of it. What that means is the following. Starting with Einstein had a lot of misgivings about quantum mechanics because he thought that there can't be just the wave function. That won't be a complete description of a system. That's what the doubts that he had. And in a sense, Bohmian mechanics is the answer to that because it puts back the ontology in quantum mechanics. It said the things that you were missing when you were just talking about the wave function is that you were not saying it was a wave function of what, or where was it defined? It was defined on the configuration space, but configuration space of what? It has to be points right? So that's so by putting the ontology back, Bohmian mechanics completes quantum mechanics. It's not just an interpretation. Bohmian mechanics is not an attempt to reduce quantum mechanics to classical mechanics by assuming strange forces. It is, Bohm is partly guilty for this, because when he came up with his theory, in order to sell it, he packaged it in this way that, oh, look, we're just like Newton's equation, but there are some funny forces in there. But that's actually not what Bohmian mechanics is. And you can see why not, because if you go back to these equations here, this is the first order equation, right? I showed you. Well, we can take another derivative here, make it a second order equation, and then use the Schrodinger equation to replace the time derivatives of psi that you would get on this right-hand side from this from the Schrodinger equation. And you're going to get some nasty looking nonlinear right-hand side here, which, okay, it's like the second derivative equals, but the stuff on the right-hand side looks very weird. So, and then you say, well, that's okay. That's why do we have to do that, right? It is not necessary to do that. This is the actual equation, the first order equation. So Bohmian mechanics is not ruled out by von Neumann's no hidden variables theorem. So it is actually a counterexample to the impossibility claims that von Neumann made. So I have to give you a little bit of a history there. So what are these hidden variables? Because Einstein, remember Einstein had misgivings about the wave function being the only thing that there is. And that would be a complete description of a quantum system. He thought there has to be other things. And in fact, Einstein, together with Podolsky and Rosen, later on proved that under a certain important assumption, that would have to be the case. Now, before that, von Neumann in the late 20s, early 30s, claimed to have proven a theorem that would rule out hidden variables. Hidden variable means anything other than the wave function, and that's there. So of course in Bohmian mechanics, what are these hidden variables? These are the positions of particles. So in a sense, that's a very poor terminology, because that's not hidden at all. It's like the only thing that's revealed is the position, and yet that terminology kind of stuck. So anyhow, von Neumann claimed to have proved this theorem. Later on, people showed that he actually has not proven what he claims to have proven, because it's a mathematical theorem. And as we know, mathematicians know, every theorem is as good as the hypotheses that go into that theorem. And one of the hypotheses that von Neumann made was so restrictive as to rule out any interesting example of hidden variables. So this was explained by John Stuart Bell later on. I did not talk about any historical things, so let me spend just a little bit of time on that. The original idea of a wave or a field guiding a particle is due to Einstein. And he talked about Einstein imagined already back in 1909 that particles of light are guided by some kind of a field. Whether it was electromagnetic field or not, that wasn't so clear. That Dobrys took that idea and ran with it. He said that maybe all particles are guided by a wave, and that wave has to be defined in the configuration of the space of the particle. So he already put that in his doctoral thesis, and the committee, the PhD committee, wasn't sure what to make of it, so they sent it to Einstein, and they asked, "Oh, Professor Einstein, can we give this guy a PhD because of this thesis?" And Einstein said, "You have to give him the Nobel Prize." So that's but Dobrys later on abandoned this idea because he was not able to answer the criticisms at the time that were made to this idea of pilot wave. David Bohm, American physicist, rediscovered the Dobrys pilot wave idea and realized that it makes empirically correct predictions. That was in 1952. In recognition of that achievement, his passport was taken away and he was kicked out of the country. Well, that's not true. This is because he got caught up in McCarthyism of that time, and he spent the rest of his life as an exile. And however, Bohmian ideas survived. Bell extended Bohmian mechanics to particles with a spin and provided further clarification of it. For example, this important thing that it's not ruled out by von Neumann's theorem. Then Detlef Dürr, Shelley Goldstein, Zangi, and their associates brought mathematical and conceptual clarity to Bohmian mechanics and made advances toward a relativistic extension of it starting in the 1990s. And that effort is still continuing. For further information, go to this website, bohmianmechanics.net, where you will find all kinds of articles and books and videos about the subject. You can subscribe to the YouTube channels QTWO3, that's Quantum Theory Without Observers, number 3, and the YouTube channel of the John Bell Institute. If you want podcast, you can listen to the LMU podcast, An Introduction to Bohmian Mechanics. These are about 15-minute long, so they're very handy to listen to. And with that, let me now stop before the next thing I want to talk about is a relativistic extension of Bohmian mechanics. But let's see if there are any questions that you would like to answer.
Could you tell us where this first order differential equation came from?
Right, that's an excellent question. So in fact, the way Dobrys came up with it was he was from Hamilton-Jacobi theory. So, and nowadays we know that it is possible to actually, let me go back to that slide for a second. So this equation, right? So we know that it is possible to derive both the Schrödinger equation and this equation together from a certain so-called least invasive quantization of a classical Hamilton-Jacobi theory. So you start with the classical Hamilton-Jacobi theory, you write an action for it, and then you deform the action by adding an entropy term to it. And then when you write down the critical points of that action, you're going to get both Schrödinger's equation comes out, and this comes out because this is a leftover from the Hamilton-Jacobi formulation. So this is actually, there's that sense in which these equations are you can, I mean, of course, you're making a theory, so you can write something else that this is my theory. But it's good that in this case, at least we can say where this thing can possibly come from.
Okay, looks like we have quite a few questions. So to Ginger.
Yeah.
You're unmuted.
Oh, yes. Thank you. I had a quick question about how do you go about deriving or justifying the Born probability rule from the initial conditions? Is that satisfactory in your opinion in Bohmian mechanics?
Yes, I think so. So I did not have room in my slides to write that equation, but you know, I'm sure you know that there is a equation of continuity that associated with this Schrödinger equation. Actually, if you, I will have that equation in the relativistic version of the theory. So you will see there how it comes about. So you can define a row and so on.
Okay, Glaucia, go ahead. Oh, let's try that again. Glaucia, go ahead.
Hello. So you were asking what this first order equation means. And this simply means that particles move along the integral curves of the probability current flow. Yeah, that's the meaning of this equation. Yeah.
Right. Thank you. Actually, I will, as I said, I did not include that here, but I have that equation and that interpretation in the next slides to come.
Yeah. So it's not something out of the blue, but it has a very geometric meaning.
That's okay. Thanks. Yeah, that's true.
Okay, Huang, let me just unmute you here. Okay, so Huang, I think you need to give me permission to unmute you. There we go. Okay, please go ahead.
Yeah, thank you. So in page number 5 here, you have the capital Q in the top equation and the little q's in the bottom equation, right? So are there any back reaction there or not? I mean, what I mean is that when the particle moves in some trajectory, right? So do they enter into the potential V in the Hamiltonian?
Well, there is no back reaction, and the way this is formulated, as you can see, right? The wave function is defined in configuration space. The particles are in physical space. That's it, like different world. They're in a different place, right? So if you wanted the particles to kind of back react on the wave function, then you would have to modify Schrodinger's equation, and we are not doing that, right? So this Schrodinger equation is the same one of the standard quantum mechanics.
No,
I think the analogy, the reason people think about back reaction is that they make the wrong analogy with particles and the electromagnetic field. So we all learned in the course of electromagnetism that particles are sources for the electromagnetic field, which then acts on the particles and moves them, and then they in turn react back on the field. But this is not the situation here, because the wave function is nothing like the electromagnetic field. It is not defined on the same space.
Right, but what my confusion is the wave function is dependent on the Hamiltonian. But the Hamiltonian depends on even have the potential term right there. The potential term, it can be, the particle can have some charge, right? It can be set in that. It's not purely scalar particle without any charge, anything. So that's okay. I mean, I think that it is if you upgrade this problem into the quantum field theory, then perhaps the back reaction would participate into the situation.
All right. Well, I don't have anything to say about that.
Thank you.
Okay, Rifat, please go ahead.
Hi. So what are the hidden variables here? Is it like the positions of the particles, which are guided by the guiding wave, are the hidden variables? Actual positions. Actual positions.
Okay. Yeah, as I said, that's a very unfortunate terminology. There's nothing hidden about the actual positions, but that's
so. Yeah. Okay. So can you go to the next slide, please? So you're saying like Bohmian mechanics is actually deterministic, and this randomness comes because like at t equals to 0, I don't know where exactly the particle is, and I assign some probability distribution for the particle for the hidden variables. Now, what tells me that this probability distribution must be the same thing as the psi star psi of the guiding wave?
The initial psi, right?
Yeah. So
it's a hypothesis. It's a hypothesis.
Okay. All right. Okay. Thank you.
Yeah, we do have hypotheses, like all theories, right? You need to have some hypotheses. But Bohmian mechanics has relatively few hypotheses.
Okay.
It doesn't have a long list of axioms about strange things.
Yes. Okay. Thank you.
All right. So I think I should go on. Cohl, is that okay?
Yes. Yes, please go ahead.
All right. Okay. So now I want to talk to you about a particular relativistic extension, and there is more than one. This is just one of them of Bohmian mechanics. So I want to start by telling you about something called the multi-time wave function. So now we are in a situation, we have n particles, and these are relativistic. Let's say you spin half for the sake of argument. And this wave function now depends on n variables. Each variable is a point in Minkowski space. So now you don't have, so previously you just had one time and n different positions. Now you have n times and n positions. That's why it's called the multi-time wave function. And So let's see if we can, how far we can go using the setup of Bohmian mechanics that I showed you. We need two equations, one for the evolution of this psi, which would be a PDE, and then we need another equation, an ordinary differential equation that would specify now the word lines, the actual word lines of these particles in physical space-time. So can we have such a theory? And the answer is yes. So first of all, for the evolution of psi, we have a very good candidate. That's Dirac's relativistic wave equation, but now the n particle version of that. So you can just, by tensoring things up, it's very easy to get an equation like that, which looks just like Dirac's equation, but for n particles. So here, you start with the familiar gamma matrices of Dirac. You form these tensored up version where you have gamma sub k is identity tensored with itself n times, except for the kth position, you put in the gamma there, plus the one body version of that, right? And now you have this Dirac operator, which is the n particle version of the one that you have seen. Okay, so that's the equation. And now, if you had just one particle, this is well known. There is something called the Dirac current, and which you can form. So this is just for one particle. So psi just a function of x1, let's say. Then you can form this psi bar. This is psi dagger times gamma naught, and then you put it in here. You form this vector, and this vector has very interesting properties. The time component of it is psi dagger psi, so it's always non-negative. And the space part, the spatial part of it is in absolute value is less than or equal to the time part. So this vector is future directed time-like or causal, actually, if you include the equal sign here. So, and it's a Lorentz vector. So now if the wave function satisfies Dirac's equation, it implies that this current is conserved. So its divergence, its forward divergence is 0, which gives you this equation, the time derivative of J0 plus the divergence of the spatial part of J is 0. Now you call rho, let rho be J0, and let Vk be Jk over J0. And now you have this continuity equation coming out here. Now you can view that as a continuity equation. This J0 is non-negative, right? If you are on the Hilbert space of square integrable functions, the total integral of this rho will be finite, so it can be normalized to be 1. So now it has an interpretation of a probability density function. And this is where Tejinder was saying that you can have this continuity equation and see that this V here is naturally the guiding velocity for the particles. So like several people. So indeed, you can write down your one particle guiding law in this way. The velocity of the actual particle at time t is this V when you plug in the position of the particle at time t. This is just for one particle. Now, if you want to do it for n particles, okay, constructing the current is not difficult. You're just tensoring things up. So you form the tensored up version of the current, and now this has n indices instead of one index. And in each index, it is divergence free. This Dirac equation up here implies that in each index it's divergence free. Remember, these are k equations. This is not one equation, right? So I've written here k equals 1 through n. For each k, you have this equation. So this psi satisfies many equations, not just one. And that's why you're going to get many conservation laws. All right, so far so good. Now, how do I get a guiding law out of this? It looks like I would still need some way of synchronizing the particles, because what I want to say is that the velocity of the ks particle is given by the velocity field when you evaluate it at the positions of all the other particles, but the question is position at which time. So now you need some way of relating or synchronizing the times of these various particles. So that's given by this thing called the hypersurface Bohm-Dirac theory. Essentially, what this theory says is that if you have a foliation of a space-time, then you can do this thing. And this is a way of synchronizing the particles. Of course, it's a valid question. Where would this foliation come from? And I will address that in a minute. But let's go along ahead with that. Suppose there is a God-given foliation, right? And later on, we will explain where we would get that, right? So if I had such a thing, then it is easy to see that I have a guiding law, because now I have k word lines, right? And the forward velocity of each one of those word lines of the word line of the kth particle is given by, you take that current which had n indices and you contract with the normal to the foliation on every index except the one, except the kth one. And leave the kth one alone, contract on all the other indices with the normal to the foliation. And then evaluate on that particular foliation leaf. Plug in for x's the intersections of the word lines with that particular foliation. And when you do that, you get a guiding law. This is the guiding law of HBD theory. Okay, so on Minkowski space, here's an example. If you have Minkowski space, you suppose this foliation is given just by the constant time slices, then you will have the forward velocity equals j with zeros in all the indices except for the kth one, right? And then you evaluate it on x1 through xn, where the x's have all the same t and different q's. Okay, so now staying with this situation, you can say let rho be equal to j with all zeros up there, and then you have, from that you get the velocity with respect to the derivative with respect to time of the position of the kth particle is given by this formula, which looks exactly like what we had seen in the one particle case, but now this is with n particles. So all of this, of course, is thanks to this foliation. We also have these continuity equations as before, so which justifies our guiding law, if you will, as was mentioned before. Now, here's what we need to talk about this foliation. Suppose this foliation is determined by the wave function. So remember that the wave function is evolving according to a covariant law. So if the foliation is determined by the wave function, right, in a covariant way, then the foliation is also evolving in a covariant way. And now we can still regard this as relativistic. This may not be the full notion of relativistic that you were expecting, but as I was saying before, we cannot have locality in our theory. That would contradict what we know about the results of experiments. So, okay, were there questions, Cohl, that I need to answer?
Yes, yes, there are. So, Wolfgang?
Thank you. Thanks for the opportunity to ask a question. So can you go just briefly back to slide number 10, please? So perhaps you could answer why, so the naive proposal for a guiding law would be that I would have assumed would be that on the left-hand side, yes, you have d over d tau x mu of k, so the position in Minkowski space of the k particle. But now you could perhaps say that on the right-hand side, I just put the current psi dagger gamma mu k psi. So why would that not work? Why do you have to work with this higher tensor, and then I have to find a way to get rid of all these indices. So what's going wrong with kind of the naive proposal that seems kind of immediate?
So psi dagger, gamma, but that I think amounts to the same thing.
Uh-huh.
That's because when you look at this thing, right, this is, I mean, if you look at this example that I gave on Minkowski space and recall what the definition of this J was, right? So maybe I go back a little bit.
Oh,
So
I see.
remember,
Yes.
you see these gammas are, this is just that, right? So, and what I'm doing here is that. So if you just get and okay, this psi bar, by the way, it's also the tensored up version of the bar. So it has all the gamma zero factors that you need in order to kill these gamma zeros. So you will end up with the psi dagger. I think this is going to be the same thing. It's just more general because it's talking about a foliation, which would then later one has to say where it comes from.
Okay, thanks.
Okay, to Ginger.
Yeah, thanks. I have a question about this time tau that you have introduced. Suppose we propose that tau is the absolute universal time parameter, like Newton's absolute time, which is over and above the time coordinate t of the four-dimensional space-time manifold of special relativity. Would there be something wrong if I did that?
Well, this tau is not time. This is just the parametrization of the this is just the a parameter. You need to parameterize these time-like curves with something. That's this tau. So that's it doesn't have any meaning of absolute time
like
or
this,
anything like that.
Not like the Stuckelberg formalism in which time in relativistic quantum mechanics made an operator, and then he needs an additional real time parameter to describe dynamics. You wouldn't say your tau is like that, is it? I think that tau has no significance here. What has significance in this is, of course, the foliation. So in some sense, this foliation is playing that role for you. What measures the flow of time from past to future, say?
Well, I mean, this is, I'm not sure how to, this is, you have, yeah, I think the foliation is doing that. So of course you can change this parameter tau, right? You can reparameterize this thing. So that itself does not have significance, but I would think that probably the vector field, the unit time-like vector field is doing that for you. That's,
okay. Thank you. Thank you.
All right, so, okay, so now I'm going to be running out of time. So how much time do I have, Cohl?
I think everybody's been running a bit over.
Okay.
Yeah, so if I don't know if you need 10 or 15 minutes.
Okay, yeah, I will take 15. No, because I mean I wanted to answer questions, but then that's then I still have to tell you what I have done. So
yes, yeah,
that's okay. So here's a little digression because we need to talk about spin. If we want to have some theory that's general enough that covers both half-integer spin and integer spin particles. So this is a short reminder of Clifford algebras and how they enter quantum mechanics. There's the Pauli algebra, which is the algebra generated by the Pauli matrices. This is the same as the Clifford algebra 3,0, which is also isomorphic to to the 2 by 2 matrices over complex numbers, and it's also isomorphic to the tensor product of C and complex numbers and the quaternions, so the complex quaternions, so to speak. Then there's the Dirac algebra, the algebra generated by the gamma matrices, right? This is the same as the Clifford algebra 1, 3, and then you can complexify it by taking complex linear combinations. And that is the algebra that I will be using in this talk. This is turns out to be isomorphic to 2 by 2 matrices over the complex quaternions. But you can also view them as tensor product of complex quaternions with themselves, and is also isomorphic to 4 by 4 matrices with complex entries. In Bohmian mechanics, spin is a property of the wave function. So I remember what particles have is position. So, and spin is not something that is in the, it's not a variable, it's not a hidden variable, in other words. A spin is in the wave function of the particle. So now, therefore, it's important to say, how do the wave functions of particles of various spin look like? So wave function of a spin half particle, this is just a reminder from what you already know, is a spin is a rank 1b spinner, meaning that under a Lorentz transformation of the base, it transforms in the following way, where L sub lambda is a representation, is the spinorial representation of the Lorentz group. And the wave function, therefore, becomes a p-valued, a complex quaternion valued B spinner field. So remember that complex quaternions are isomorphic to 2 by 2 complex matrices. You have these projections, right? So you can, and then if you apply them from the right, you can decompose every psi in P into a psi left plus a psi right. Basically, if you think of a 2 by 2 matrix, either you can have the right column 0 or the left column 0, and that will be psi left, and the other one is psi right. And these two things are minimal left ideals of the algebra P. You can embed this in A, in the bigger algebra, by just multiply, say, psi left by sigma 1, it moves this column to the right, it aligns it with this one, so you can put it here, and now you have some element in the 2 by 2 matrices over the quaternions, which is isomorphic to A. And as x goes to lambda x, we apply a Lorentz transformation of the base. Now psi is going to be transformed in the following way, where I've used here the notation that I learned from Cohl's thesis about two-sided action of the algebra. So this is just a review of what we know. Now, what about the spin 1 and the spin 0? Well, these are rank 2 B spinners. So they transform in the following way. When you change the Lorentz transform of the base, the wave function transforms in the following way with factors of L lambda on the left and L lambda inverse on the right. So that's the difference with the half integer spin. The wave function is an A-value tensor field now. So now it's just an element of the big algebra is your wave function, which is 4 entries being quaternions. And the diagonal blocks, this implies that the diagonal blocks transform in this way. The off-diagonal blocks transform in this way. So now you can take each one of the diagonal things and separate the trace out. And the reason I'm doing that is you realize that, let's say, look at the transformation of phi plus. It is A on the left and A inverse on the right. If phi plus is a scalar, A and A inverse will cancel each other, so that phi plus, a scalar phi plus, will remain the same, will be invariant. So if I take off the trace part of this, that's the part that will be invariant, okay? So now I claim the spin 1 sector of this is where you have the diagonal blocks have trace 0. So that will be the spin 1, and the spin 0 are the ones where the diagonal blocks are just complex numbers. In other words, the trace part. So notice that this means that these really transform like scalars, as you would expect from a spin zero field. Now you may think that this is more than what is expected to have. The spin degrees of freedom for a spin s particle is supposed to be 2 times 2s plus 1. So for s equals 0, it should just give you 2, but here there is more because there is this chi thingies. So now I will show you that these off-diagonal things are actually auxiliary variables. They are not independent degrees of freedom of the wave function. That depends on the equation that these things satisfy. So one has to take the equation into account. And I claim if you take the equation that this thing has to satisfy, the evolution equation into account, it will turn out that the off-diagonal parts are not independent. And therefore, for the diagonal parts in the spin 0 case, you just get 2 components. And in the spin 1 case, you get 6 components because these 2 phi plus and phi minus, recall, these are 2 by 2 matrices, each one of them, and their trace is 0. So that leaves you with 6 degrees of freedom. Okay, what equation these satisfy? Well, the Dirac operator, you've already seen it. The Dirac already said that the wave equation for a massive spin half particle should be the following. This you know. And this implies in particular that each component satisfies an equation with this d plus and d minus here, like that. So you can see the 2 components are coupled to each other because of that. So in 2018, together with Michael Kiesling, we proposed the following wave equation for the photon, which is a massless spin 1 particle. So it looks like the Dirac equation here, but remember this psi is now an element of the algebra itself. So this is a matrix equation. And here I have some projection applied to psi. This is a projection onto the diagonal blocks. And I need to include some parameter here for dimensional reasons, but this is not the photon mass. You will see that this is really is describing a massless particle. Let's see how that works, because you can work out what this means, and you see that the diagonal blocks themselves, it's a consequence of this equation. The diagonal blocks satisfy the massless Dirac equation, and the off-diagonal blocks satisfy an inhomogeneous equation. And that's very important. So this is what I was saying before. So these are just independently, you can solve these, right? The phi's. And once you have the phi's, you can put the phi's here, and now we can solve for the chi's. So in this sense, the phi's determine the chi's. So the diagonal components determine the off-diagonal components. So that's what I was saying before. You can also go into a frame where the phi's have the following form: two vectors in R3. So each phi plus or phi minus is I sigma dot E plus IB. So that, and when you write these equations in terms of these E and B, you see that they satisfy Maxwell's source-free equations. So Maxwell's equations, so actually a pair of Maxwell's equations are hidden inside this equation, which basically tells you that it has all the properties, all the right properties to be guiding a photon. So we also need a probability current for the electron. You've already seen it. We need one for the photon. So, and we also need a foliation if you want to do hypersurface Bohm-Dirac. So both of these are addressed here. Let's look at the projection on the diagonal blocks. Then, as I said before, that satisfies the massless Dirac equation. There's an object called the Riesz tensor. It was discovered by Marcel Riesz in 1946. You can form this tensor out of this solution of any solution of a massless Dirac equation. And it will have these properties. It will be symmetric. It will satisfy the dominant energy condition. And it's divergence free. So these are basically all the familiar properties that you have seen for the energy momentum tensor. This thing replicates that. And now if you take any Lorentz frame, coordinate frame, and you look at the tau mu nu, if you integrate the component of t dot n over a constant t slice, you're going to get with these quantities pi coming out. And these, even though it looks like they depend on t, you can prove, because this is divergence free, you can prove that these pi's are constant. So this vector pi will be a constant future directed and causal vector. This is all thanks to the properties of the Riesz tensor. Well, if it's not null, which generically it won't be, because this being equal is a exceptional condition, you can normalize it to get this vector x. And if you plug this vector x here with tau, if you contract with tau, you get a current. You get a conserved current. And you can also use the same x to construct the foliation of the spacetime by hyperplanes. This foliation is determined solely by the initial wave function. So this is what we were after, because we were after a foliation that's determined by the wave function. So now you can use hypersurface Bohm-Dirac theory to find photon trajectories. In one dimension, the diagonal part is 0, but now in one dimension, the psi itself can be used because it satisfies the massless Dirac equation in one dimension to form the tau. So now you can also do this theory in one dimension. And I will just briefly show you what we've been able to do this in one space dimension. You have a photon and an electron. The two-body wave function is the tensor product, so it has 4 components. You write down the equations, the photonic equations, massless photonic equations, and massive electronic equations. These are the multi-time equations I was talking about. This is okay because these two operators commute. We need to specify initial data. We also need boundary conditions on the places where the particles are at the same time, at the same location in the space. So as to prevent them from going through each other, because we are doing Compton scattering. This is what we are doing. We're modeling Compton scattering in this way. So I'm going to solve these equations together with some initial wave function, and turns out this is the boundary condition that does that. And we proved together with Matthias Lienert and Michael Kiesling that this problem is globally well posed, and you get a solution that's Lipschitz continuous everywhere. And for typical initial configuration of the particles, the trajectories for the photon and electron exist globally. And if you start with one to the left of the other, they will remain like that. So they won't go through each other. And I can show you some video of how this thing looks like. So, so first of all, so this video was produced by my assistant, Hali Bayat. And what you're seeing here is the joint probability distribution of a photon and an electron. So this direction is the photonic direction, and this direction is the electronic direction. You start with a wave function concentrated at one point. It has 4 components. As time goes by, these 4 components separate. One component hits the boundary and bounces back. And that gives you the interaction between so because of the boundary condition that we have put in here, when one component leaves, another thing enters the domain to sort of, this is how the probabilities are conserved in this. So now you have the wave function. This, if you want, is the movie plot of the wave function, the two-body wave function. You can use that to see what the trajectories look like. And when you solve the equations that I showed you, you see that the blue line is the electron and the red line is the trajectory of the photon. They enter the interaction zone and they bounce off one another as you expect them to do. And you can now repeat this for many initial positions of the photon and electron distributed. And you see this kind of dance where the now you have pairs of trajectories, and sometimes they go in opposite ways, sometimes they all go in the same way, but when they come towards each other, they bounce off one another. What you would expect from a scattering picture to look like. Okay, so conclusions. Bohmian mechanics is a theory about endpoint particles in space whose motion is guided by a wave function defined on the end particle configuration of space that evolves according to the linear Schrödinger equation. Hypersurface Bohm-Dirac theory is a relativistic extension of Bohmian mechanics in which, given a foliation of a space-time, one can use the conserved tensor current associated with the multitime wave function of a system of n particles to find the world lines of those particles. Photons, too, can be viewed as particles guided by a Clifford algebra valued wave function that satisfies a Dirac type equation. One can use the conserved Riesz tensor of this wave function to single out a particular foliation of the Minkowski spacetime by Hartle planes and use the hypersurface Bohm-Dirac theory to find the photon trajectories. Interactions of photons and electrons can in principle be entirely understood in terms of particle interactions. Much, of course, remains to be done here, and we need your help. If you are a recent PhD in physics or math and are interested in working on fundamental physics, consider applying for a postdoc position at Rutgers, which is advertised at mathjobs.org. And with that, let me thank all of my wonderful collaborators in these projects. We have a wonderful team of talented and diverse group of people, including my longtime colleague and friend, Michael Kiesling, our amazing postdoc, Eric Ling. He is on the market this year. Our former postdocs, Maneli Darakshani and Matthias Lienert. My current PhD student, Larry Frolov, and these are all the undergraduate researchers that are involved in my project, Stephanie Zhou, Max Wang, and Adriana Scintiano, graduated this year and moved on. Marcus McLaurin is a graduate student at Morgan State. Sam Lee is a physics major here at Rutgers, planning to go on graduate school in physics. And Holly Bayat is a senior math major at Georgia Tech. Thank you all for listening.
Okay, well, thank you so much, Shadi, for a wonderful talk. I believe, yeah, I think you might have some questions. So, Wolfgang, you've got your hand up. Let me unmute you. Wolfgang?
Sorry, I just kept my hand.
You forgot to put it down. Okay, no problem. Okay, so let's see. Next, to Ginger.
Yeah. Thank you. A very beautiful talk. I really enjoyed it. I'm a big supporter of Bohmian mechanics. There are a couple of questions comparing Bohmian with collapse models. Firstly, your general thoughts, because Bohmian has randomness in initial conditions, collapse model has it in the dynamics. Do you prefer one or the other? And the other question was, you have a very good experimental test from arrival times, which would distinguish it from normal quantum mechanics. What do collapse models have to say about this particular kind of experiment? They would agree with quantum mechanics and hence have a problem in explaining arrival time? I did not realize this until I heard your talk today.
So, okay, to answer your first question, I think the answer to the first question is obvious. I prefer Bohmian mechanics. And the reason I would say is that in the collapse model, you have to modify the equations. You have a different equation. Yeah, you don't have Schrödinger's equation anymore. So, and I think that's a departure that I'm not prepared to take. Of course, it could be that's what it is, but anyhow, and I think I think it's a very interesting way to think about it, and I would suggest that maybe you invite someone who works on collapse models talk about it, or maybe you are already doing so, Cohl. I don't know.
Maybe Angelo Bassi is the best.
Yes, but there are many, but yes. So and also regarding your second question, again, I'm not the right person to ask about that. I think that arrival times, it's a very natural thing to study within Bohmian mechanics. It doesn't present any problems, and I would not know how other approaches would address the same thing.
Okay, thank you very much.
Okay, Nosrat, go ahead. I'll try unmuting you again here. Okay, there you go.
One question is about what is exactly the meaning of the non-locality here?
The exact meaning is what I mentioned in the beginning of the slides, which is that the velocity of the kth particle depends on the positions, on the actual positions of all of the particles. And that dependence does not necessarily go down with distance.
And the second question is this: if Bohmian quantum mechanics complete the quantum mechanics, is there any result that in the Bohmian mechanics that we cannot find in the normal quantum mechanics? What is the benefit of the
Right. So I briefly mentioned that. So for example, in the study of arrival times, you can see that. So I urge you to look at that article, that Scientific American article, or just, you know, look into what one can do with a question of arrival time statistics. That's one area in which one could. There's even in that article, there's even mentioned possibility of an experiment that could be able to settle this question.
Thank you.
Okay, Torsten, go ahead. We'll try that again. It seems to take 2 tries every time. Okay, Torsten.
Okay, yeah, right. Maybe first one, is it possible, or is there any effort to understand this non-locality condition or the non-locality potential of velocity in a sense of topology? Because one knows, for instance, take Morse theory and topology, you have also a globally defined function on a manifold, and taking the critical points determine in some sense the topological structure of the whole manifold. So you have also a function defined on whole parting, and then getting also such a also accept local expressions like the critical points, determining then the global topology. And the second question is about, you start with the Clifford algebra. Did you also try to make it more general instead of the Minkowski metric, put a Lorentz metric of a general manifold? Then you get maybe another condition on this equation, and then you get also in some sense a coupling to geometry or then to general relativity. Is that also an idea which you follow? Yeah, these are the 2 questions.
Well, big questions. So regarding topology, I don't quite see how this could come in what I talked about. That is not to say that topology is irrelevant. In fact, we do have a proposal that would explain matter-antimatter symmetry using topology, using non-trivial topology of a space-time. So I do believe that topology has something to say, but I'm not sure if it relates to this particular thing that you mentioned. So that's requiring considering the first question. Regarding the second question, of course, Bohmian mechanics, although I love it very much, it's not the final theory of physics. We have not put in gravity into this theory, and I think any consideration of using a metric, a Lorentz metric of the space-time, cannot be separated from considerations of how is gravity going to come in to this picture. So I think that's something. Also, of course, we have studied what we have studied with my colleague Michael Kissling and Eric Ling. We have put Dirac's equation on a solution of Einstein's equations. So not on Minkowski space, but on something else, right? And study the behavior, the spectrum of that operator, right? And this, so things like that you can do. Yeah, we have done that. But I think that is still kind of different from the question that you asked. I think the question that you asked is deeper.
Okay.
And would require basically extending all of this to include also gravity.
Okay.
And that, of course, we have not done yet.
Okay, maybe some additional comment. You spoke about that randomness is the source of randomness is that we don't know the initial conditions. Maybe I disagree a little bit, because all this discussion of Boltzmann and the scattering integral and showed that you in that time Boltzmann thought that he find the source of randomness and all that and like, but if you analyze this integral, the scattering integral of him, where he showed the growing of entropy and such things, is that he made some implicit assumption on randomness or on such things in an initial condition. So I think randomness today, or most people believe that randomness is something deeper in the whole configuration space, or deeper in physics, and it's not only a problem that you don't have the whole knowledge of the initial conditions. Maybe you disagree, but
well, I think I disagree, but I think this is probably not the right forum to opening that study. That's a very important subject, and we probably have to devote a whole other presentation to
of course
this question. That's because I agree that that's a very deep question, and there are different points of view, and people can, and also I'm not the expert in that, but I know the experts in that, okay. So I talk to them. So I think we could. This is definitely something that should be explored further in a separate
from the initial point of view. Okay, good. Thanks for the great talk. So it's okay.
Okay, Andras. Okay, go ahead.
Okay, so can you go again to slide 5, maybe? Just to have some guidance. So you mentioned that basically we very nicely explained there the let's say the basics of Bohmian mechanics, that basically it could be Dirac equation even, so it doesn't need to be non-relativistic. So your basically Dirac equation, so to speak, will define you a probability current vector field on the space-time, and then the motion of particles are basically guided by the integral curves of this vector field. Now, what happens if we are in a mixed state? Do we have a corresponding notion of probability current vector field?
Well, there is a so by mixed state, what do you mean by that?
Well,
so
this equation of motion, I mean, for example, Dirac equation, Schrödinger equation on the wave function is about pure states, right? And but
no, it's not. I mean, this is the wave function of the system, right? So that's this could be a pure.
No, I mean, if the system is described by a density operator and not by a rank one.
Okay, yeah, the density version of this. That's what you mean.
Yes.
Yes, there is a density version of this.
All right. So it can be reformulated in that terms as well.
Yes, you can formulate.
Thank you. Thank you.
Okay, Rifa, go ahead. Oh, 2 tries.
Okay. Hi.
Were you saying that Bohmian mechanics is a completion of standard quantum mechanics because standard quantum mechanics does not explain the arrival time?
No, by completion, I meant that the standard quantum mechanics denies that there are particles and that they have positions. So it's a completion because it puts back the ontology in the theory. That's what I meant.
Okay, right. Thank you.
Okay, Hillary, go ahead.
I just wanted to ask, what does your approach have to say about tunneling times? There's some very interesting experiments by from Steinberg's group looking at this, and you'd have thought quantum tunneling, where you, according to the experiment, seem to be getting superluminal speeds, and yet this does not cause all the problems that people normally say will happen if there's superluminal speeds. So presumably, Bohmian mechanics actually handles all that and makes that problem go away. I don't know how exactly, but whatever. I was going to ask you, what does Bohmian mechanics have to say about this question? Because it would seem to be a whole area in which the conventional standard approach to quantum mechanics gets into difficulties.
Unfortunately, I don't know about this. Sounds like something I should be looking into, but thanks for mentioning it. But I have not looked at this thing that you mentioned.
Ephraim Steinberg had a science paper fairly recently. It might be in the last couple of years or so. So really,
can you put it in the chat, the names?
Pardon?
Can you put the names in the chat?
There is no chat.
Possible? Oh, okay. So just okay. So you said what were the names?
I can try and dig out the reference for you. It's a recent paper in Science by Ephraim Steinberg.
Okay. So I would appreciate if you send it to me. That would be great.
Oh, you're welcome. Some wonderful references in it as well. So it's a great guide to the literature.
Thank you. Yes.
Okay, so now might be a good time to close things off. It doesn't look like there's any more questions. Thank you so much, Shadi, for a wonderful talk. Before we go, I should mention that in 2 weeks' time, we have Howard Barnum speaking on Jordan algebras and their role in quantum theory. And as you likely know, Howard is a leading expert on this topic. He will also be giving our last seminar before Christmas break. So I hope to see everybody again in 2 weeks.
Thank you.
Yeah, thanks again, Shadi. Just stop recording here.